All right, let's finish off section 7.2. So this is natural logarithmic and exponential functions, part 2. So something that we did in the part 1 of section 7.2 was we looked at the graph of natural log x. There it is. And we've already discussed these facts about natural log x. Its domain is 0 to infinity. Its range is negative infinity to infinity. The function is continuous, increasing, and 1 to 1. The graph's concave down everywhere. And the limit as x approaches infinity of natural log x is x. And the limit as x approaches 0 from the right of natural log x is negative infinity. So before I go on, since the function natural log x is a 1-to-1 function, it has to have an inverse function. And the domain of the inverse function has to be negative infinity to infinity. And the range has to be 0 to infinity. Items that we reviewed about inverse functions in section 7.1. So again, we know it's 1-to-1. It has an inverse function. We just said what the domain would equal and what the range would equal for the inverse function. I already mentioned that. The graph of f of x equals ln x and its inverse function, well, it's shown over here to the right. So the blue graph, that's natural log x. And I put in the green dashed line. I put in, that's y equals x. Because remember, the graph of a function and its inverse function will be symmetric about the line y equals x. So the red graph, that is the graph of the inverse function of natural log x. And it has a name. The inverse of f of x equals ln x is g of x equals e to the x. So e to the x, that is the inverse for natural log x. And here's a little fact you might remember from algebra. Y equals e to the x if and only if the natural log of y is equal to x. So that's like a little algebra fact. Since the inverse of f of x equals natural log x is g of x equals e to the x, and since we know f and g are inverses, remember what we reviewed in section 7.1. The composition f of g of x must be x, and g of f of x must be x. So if I go through the compositions for f and g, so if I do f of g of x, and then I do g of f of x, it will give us the following two facts. That natural log of e to the x simplifies to x, and e to the natural log x simplifies to x. Here are three more properties, and these are just basically from the rules of exponents that you would have learned way back in algebra. So e to the x times e to the y, when the bases are the same and you multiply, you add the exponents. E to the x divided by e to the y. Well, when the bases are the same and you divide, you subtract the exponents. And then e to the x, all of that raised to the y power, well, you multiply the exponents to get e to the x times y. Let's review a few properties of just e to the x. So there's the graph of f of x equals e to the x. We know what its domain is, all real numbers, and its range is 0 to infinity. We know e to the x is continuous, it's increasing, and it's 1-to-1. But look at the graph. The graph of f of x equals e to the x is concave up everywhere because tangent lines would be below the curve. Couple of limit statements. The limit as x heads off to negative infinity of e to the x is 0. And the limit as x heads to infinity of e to the x, well, that's infinity. All right, since natural log of e is equal to 1, that implies that the integral 1 to e of 1 over t dt, that also equals 1. couple more things about e. It's an irrational number. It's probably the second most famous irrational number. I think pi is probably the most famous irrational number. So remember, this is a number that goes on forever and ever. It doesn't repeat. If you use a calculator, you'll see e is about 2.718281824, and it goes on forever and ever. Now we know pi is exactly equal to the circumference of a circle divided by the diameter of the circle. Similarly, e is exactly equal to the limit as x goes to infinity of 1 plus 1 over x to the x power. I can't convince you of this fact right now. In a couple of sections, I'll be able to when we revisit an old topic, L'Hopital's rule. But I just wanted to give you that fact right now. That's exactly what e is equal to. So folks, the time has come to determine a new rule, a new derivative rule. The derivative for g of x equals e to the x. It's kind of an astonishing rule, to be honest. I'm gonna have to do this on my chalkboard. But before I head to the chalkboard, here's a few items that will be used in coming up with the derivative for e to the x. I am not going to use the definition of the derivative. I'm going to use stuff that we already know. For example, we know f of x equals ln x and g of x equals e to the x. We know they are inverses. We know the derivative of ln x is 1 over x. And in the last section, in section 7.1, we learned that if f has an inverse function g, then the derivative of g prime of x, equals 1 over f prime of g of x. So you may want to make a note of, because I'm going to use these facts so I don't have to use the definition of the derivative to try to come up with the derivative rule for e to the x. So you may want to write these down because I'm heading off to the chalkboard now to determine the derivative of e to the x. And it's kind of astonishing. All right, on the previous slide, there were a lot of things that I reminded us of, and I didn't write it all on the board, just the highlights. F of x is natural log x, and g of x equals e to the x. They're inverses. And we know the derivative of ln x is 1 over x. So to get the derivative of e to the x, to get g prime of x, not going to use the definition of the derivative. Instead, I'm going to use what we saw in section 7.1, that g prime of x equals 1 over f prime of g of x. So let's do that. G prime of x equals 1 over f prime of g of x. Well, that's 1 over f prime of, g of x is e to the x. So we have to evaluate f prime at e to the x. So f prime of e to the x is found by taking e to the x and tossing it into f prime wherever we see an x. So that's 1 over e to the x. 1 divided by 1 over e to the x simplifies to e to the x. And at this point it's like, well, wait a minute. Okay, what just happened? We're saying that for the function e to the x, the derivative is e to the x. It's kind of astonishing, and it's absolutely true. E to the x is a function that is its own derivative. It's the easiest derivative rule out there. Well, other than the other function that you currently know that is its own derivative, and that would be the function f of x equals 0. But yeah, because the derivative of a constant is 0. This is absolutely astonishing. Let's head back to the slides and put it in a theorem, and then I'm sure we're going to practice. I'm sure we're going to see functions other than just e to the x, like maybe e to the 3x or e to the x squared. But I wanted to do this at the board. I wanted you to see this is an absolutely astonishing mathematical fact. The derivative of e to the x is e to the x. Well, let's head back to the slides. All right, we just derived that the derivative of e to the x is e to the x. It is a function that is its own derivative. Up until this point, you only knew of one function that was its own derivative, and that would be the function f of x equals 0, because the derivative of a constant is 0. But now you know another one, and I'm going to put this into a theorem. So part 1 of the theorem is the derivative of e to the x is e to the x. So for free, I'm doing this immediately. For free, we know the antiderivative of e to the x is e to the x plus c. Now let's look at this. This is the continuation of the theorem. If u is a differentiable function of x, so part 3 here, it's like the chain rule. When you d dx e to the u, the derivative is e to the u times du dx. So think of it this way. You have e to something. The derivative is, well, the same function times the derivative of the exponent. And then part 4, the antiderivative of e to the u is e to the u plus c. So in my first example here, we're just going to practice derivatives. It's going to be 4 parts here. Make sure you write down all 4 parts because I'm going to head off to the chalkboard and I'm going to work through each one of these, and then I'm going to ask you to practice a couple from the exercises. So write them all down because I'm heading off to the chalkboard to do them. All right, folks, going to practice doing some derivatives of exponential functions. Part A. F of x equals e to the x squared. So the derivative starts off as e to the x squared. Then you have to remember to multiply it by the derivative of the exponent. That's the chain rule. Do the derivative of the exponent, which gives you 2x. Or if you prefer to write it as 2x e to the x squared, that's fine. That's it. That's all there is to it. Part B. Well, f of x equals 4e to the 3x minus 3e to the x plus e to the negative 2x. So we just do term by term differentiation. So we'd have 4e to the 3x times the derivative of the exponent, which is 3, minus, well, the derivative of 3e to the x is 3e to the x. And then this derivative, well, it's e to the negative 2x times the derivative of the exponent, which is negative 2. And I would clean this up just a little bit. I mean, 4 times 3 is 12. And here, why don't I write that as a minus 2e to the negative 2x. And, oh, we had a part C and a part D. So let me grab my microfiber cloth and do a little erasing here so I can get part C up here. So let's see here. Part C was f of x equals e to the x over e to the 2x minus 1. All right, we have to use the quotient rule. So let's take our time with it. Quotient rule says derivative of the numerator, well, that's e to the x, times the denominator, minus the numerator, times, okay, the derivative of the denominator is e to the 2x times 2, don't forget the chain rule, all over the denominator squared. Why don't we clean this up just a little bit? You could distribute the e to the x here to get e to the 3x minus e to the x minus, okay, e to the x times e to the 2x. Well, that's e to the 3x. And since we did that, we might as well combine like terms in the numerator. So you have e to the 3x minus 2e to the 3x. So that's negative e to the 3x minus e to the x all over e to the 2x minus 1 quantity squared. That's enough simplifying for that one. Part B, part D. I gotta erase this to get part D up here. Should have done that when I was putting part C up. So part D, see, the function was f of x equals x squared e to the negative x. So here we have to use the product rule. You have two functions multiplied together, x squared and e to the negative x. So the derivative is the derivative of the first function times the second function plus the first function times the derivative of the second function. Negative 1 comes from differentiating the exponent. Just don't forget the chain rule. And yeah, I could write this as 2x e to the negative x minus x squared e to the negative x. There are two of them I want you to practice in the book. So section 7.2 exercises. I want you to go to 7.2 exercises, pause the video, do numbers 32 and 36, and you know, as always, once you finish them, restart the video. I'll be here at the board working through them. All right, number 32, differentiate with respect to x 2e to the x minus 1 over 2e to the x plus 1. So we have to use the quotient rule. So here we go. Derivative of the numerator is 2e to the x times the denominator, 2e to the x plus 1, minus the numerator, 2e to the x minus 1, times the derivative of the denominator, which is 2e to the x, and all of that over the denominator squared. Yeah, I want to clean this one up a little, because when I take 2e to the x and multiply it, I distribute it in here. So 2e to the x times 2e to the x, that gives me a 4e to the 2x, and then plus 2e to the x. So when I take the negative 2e to the x and distribute it in there, I get a negative 4e to the 2x plus a 2e to the x. And that's all over the denominator squared. And the reason why that jumped out at me right away to do that was I could see that these are going to cancel out. When I combine like terms in the numerator, they cancel out. So I'm left with a 4e to the x over 2e to the x plus 1 quantity squared. Hopefully you got that. 36. The derivative with respect to x of cotangent e to the x. Well, we start off with the derivative of cotangent. We know the derivative of cotangent is negative cosecant squared. So we have negative cosecant squared of e to the x. Now the chain rule times the derivative of e to the x. Well, that's just e to the x. And if you prefer to write this as negative e to the x cosecant squared e to the x, I mean, that's quite all right. So let's head back to the slides and see what's next. I don't know, maybe some integration. All right, now that we've practiced computing derivatives, yeah, it's time to practice doing some integration. So I have 4 of them here we're going to do. So there's A and B, write them down. There's C and D. And we're going to see that, U-substitution is going to be important again. And this takes me back to when we first learned U-substitution. I gave you guidelines on, what to let U equal. And I remember telling you at that time that guideline number 2 and guideline number 3 you would see in a future chapter. Well, this is the future chapter. So we're gonna focus on what I said way back when we first did U-substitution. So we're gonna head off to the chalkboard to do these 4, and then we're gonna do one more. So make sure you write this down. We're gonna come up with a useful rule as long as b doesn't equal 0. We're gonna develop a rule for integrating e to the bx dx. So once we know this rule, we'll be able to in one step just write down, what the antiderivative of e to the 3x is, for example. So write this all down because I am heading off to the chalkboard to do them. All right, here we go, an example of some integrating. And I'm reminded of section 5.5 when we first learned U-substitution. It looks like, we're using one of the guidelines I gave you, specifically to integrate e to the negative x to the 4th, negative 4x cubed dx. One of the guidelines was try letting u equal the exponent. Well, that's the exponent. du is the negative 4x cubed dx. So when I substitute, I have e to the u, and it just so happens that the negative 4x cubed dx is, I can substitute du for that. You don't get easier integration problems than the antiderivative of e to the u, because it's e to the u. And then you substitute, resubstitute, done. Part B. We're integrating e to the 2x over 1 plus e to the 2x. So now, I'm thinking of my guidelines of U-substitution, and I don't think letting u equal 2x, that's the exponent, is really going to help here, because it's just going to turn it into an e to the u over 1 plus e to the u. However, I think the guideline that says try letting u equal the denominator, I think that's going to help. du is, the derivative of this is e to the 2x times 2. So when I substitute in, my denominator's u, and the e to the 2x dx, well, that's just 1/2 du. So I substitute 1/2 du in for that. I rip the 1/2 out front. Antiderivative of 1 over u is natural log absolute value of u. I resubstitute. And that's what I get. Now folks, I think there's probably like a 60% chance, if this were an odd numbered exercise and you looked in the back of the book, I think there's a 60% chance that the back of the book might have this as the answer. They wouldn't have the 1 plus e to the 2x inside absolute values, they'd have it inside of parentheses. And this would be an okay, correct answer for this problem. And that's because 1 plus e to the 2x is always positive. For all values of x, it's going to be positive. So the absolute values are, I guess in a sense, they're kind of like overkill, because we know it's always positive. So, would you be wrong if you had this? Absolutely not. This would not be wrong. But I thought I'd better point that out to you in case you see that in the back of the book. We have a couple more parts to this example. So bear with me as I erase the board and I get part C and part D up here. So part C was integrating e to the x minus e to the negative x over e to the x plus e to the negative x dx. Part D, integrating e to the tangent 2x secant squared 2x dx. So here's what I'd like you to do. I would like you to pause the video. I would like you to do parts C and D. Once you've done them, restart the video. I'll be here at the board working through it. Hopefully you have correct answers. So pause the video and do parts C and D. All right, part C. Here's what I hope you did. I hope you let u equal the denominator. Then du is, okay, the derivative of this is e to the x minus e to the negative x dx. So when I substitute in, let's see, I substitute in my u, so that's the denominator. And then, oh hey, that's pretty nice. Du gets substituted for everything else. I didn't have to do any massaging. That's really nice. Antiderivative of 1 over u is natural log absolute value of u. Resubstitute. And hopefully that's what you ended up getting. Part D. All right, part D. Hopefully you tried a U-sub. Hopefully you tried letting u equal the exponent. Because the derivative of tangent is secant squared. Oh, and don't forget to do the derivative of 2x, the chain rule. So that gives you a 2 there as well. So you substitute in, so you have e to the u. And then the secant squared 2x dx, well, I'm going to substitute 1/2 du. I take the 1/2 and rip it out front. And the friendliest antiderivative there is, the antiderivative of e to the u is e to the u. Resubstitute. And hopefully that's what you got. All right, folks, there was a part E here. So just like we saw in part 1 of the video, we came up with a nice little shortcut formula for integrating a over mx plus b, m not equaling 0. We're going to do the same thing right now. That's what part E is. Let's see if we can come up with a nice little shortcut formula for the antiderivative of e to the bx dx, b not equaling 0. So if we're going to do this, well, let's substitute. Let's let u equal bx. Then du, well, the derivative here is just the b times dx. So we substitute in, we have e to the u. We still need to take care of our dx. Well, 1 over b du, that is dx. So we substitute 1 over b du in for dx. Put the 1 over b out front. We get 1 over b e to the u plus c. 1 over b e to the bx plus c. So it looks like we have just developed a new little formula, which is going to come in handy, trust me, that the antiderivative of e to the bx dx is 1 over b e to the bx plus c. I mean, it's such a time saver. So if you see the antiderivative of e to the 3x dx, just knowing this, you immediately have the antiderivative is 1/3 e to the 3x plus c. Done. Or if you see e to the negative 2x dx, you immediately have the antiderivative as negative 1/2 e to the negative 2x plus c. Done. So it's a nice little handy formula to know. It's going to be a big time saver in the future. So hey, let's head back to the slides and see what the final topic is in this section. All right, you're probably seeing why I broke this section into two parts. There's a lot of information in this section, and we developed a couple of specialized rules also that you won't find in the book. But there's still one more topic in this section. The final topic in this section is called Logarithmic Differentiation. And I decided to add one more exercise. So please add number 65. I want you to do number 65 in addition to all the other exercises I've listed for section 7.2. And really, folks, the best way to see what logarithmic differentiation is all about is through an example. So in this example, we're going to use logarithmic differentiation to differentiate the following functions. In part A, f of x equals x raised to the x power. So it's x to the x. X to the x has a name. You know, in the math community, some people call the function x to the x. Some call it the tower function. Other people call it the super exponential function. That's kind of fun to say, super exponential. Then in part B, we're going to use logarithmic differentiation to differentiate the function x raised to the sine x. And the only way to come up with the derivative for these two functions in parts A and B is using logarithmic differentiation. So let's head off to the chalkboard and let's see what logarithmic differentiation is all about. All right, the final topic here in section 7.2 is called logarithmic differentiation. And I said this is best handled by looking at it through an example. So here's the function. F of x equals x to the x. You know, there are some people that call a function of the form x to the x. Some people call it a tower function. Other people call it a super exponential function. So I just thought I would give you those two names for it. To get the derivative for this, I'm going to use logarithmic differentiation. And with logarithmic differentiation, the first thing you do is take the natural log of both sides of the equation. So we take the natural log of both sides of the equation. Now notice on the right side, you can use a property of logarithms, one of the laws of logarithms, to move that exponent out front. Now I differentiate with respect to x both sides of the equation. So I'm ddxing the left side of the equation, and I'm ddxing the right side. Okay, over here on the left side, you have the natural log of some function of x. Well, we know the derivative starts off 1 over f of x, and then times the chain rule, the derivative of f of x, which we denote f prime of x. On the right side, we have to use the product rule, because you have two functions multiplied together. So the derivative of the first function is 1 times the second function plus the first function times the derivative of the second function. And let me pull it up here. And as I pull it up here, let me do a little cleanup on the right-hand side. X times 1 over x is 1. Okay, so we're trying to get the derivative. We're trying to get f prime of x. So all I have to do is multiply both sides of the equation by f of x to get f prime of x equals f of x times natural log x plus 1. Better put that inside brackets. And then there's one substitution. What was f of x? We have an f of x here. What was f of x? F of x was x to the x. So substitute x to the x for f of x, and that's the derivative using logarithmic differentiation. So part B, you had the function f of x equals x to the sine of x. Well, folks, I want you to do part B. I just did one example here of logarithmic differentiation. That's the process. Take the log of both sides, use a property of logarithms, differentiate, and away you go. So I want you to pause the video. I want you to try part B, and as always, when you're done, I'll be here at the board working through it. All right, let's see how you did on part B. We're going to get the derivative of f of x equals x to the sine x. So first step, take the natural log of both sides. Then on the right-hand side, we use a property of logarithms to bring the sine x out front. Differentiate with respect to x, both sides of the equation. Over here on the left side, derivative of natural log f of x is 1 over f of x times, don't forget the chain rule, f prime of x. On the right-hand side, yeah, we have to use the product rule. We have two functions multiplied together. So the derivative of the first function times the second plus the first function times the derivative of the second. And then I have to pull it up here because I run out of room. And I'm doing one little cleanup step. Writing sine x times 1 over x is sine x over x. Now I multiply both sides by f of x. And then finally, f of x was x sine of x. So substitute x sine x in for f of x. And that is it. Hopefully you got that. So, all right, folks, that ends section 7.2, part 2. I think you see why I split it into two separate videos. There's a lot of material in this section. But at this time, you can do all the exercises that I've listed for you to do in section 7.2. So head off and do all of those exercises in section 7.2. Thanks for watching.